stick my lead ball on right there. Okay, so now I need to even out that side with pennies. This is almost exactly level. Okay, so I think that 5 is going to be a good number to test. So, what we need to do now is obviously do our launch. Alright, so the overall idea of this is when this is launched, or my multiple projectiles, they will stick on the tape. After I take my measurement in inches, I will then record my inches, and then I will put a mark of tape down on the ground. So here's lead ball trial 1. 14 inches actually. We're looking at 14 and 3/4. Trial 3. And that one, good one. 16 and 1/4. 5 cents. Trial 1. 18.4 inches. Trial 2. 3, 2, 1. 18.5. $17.9. So over here, this is what I got. I have groupings right here for the lead, and right here is the grouping that I got for the pennies, okay? For the lead, the average was 15. For the pennies, the average was 18.26 repeating. So if you look at that, we see a pretty resounding pattern. Pennies always went a little bit higher, but not very much. Lead just stayed below a little bit, so the single lead piece was actually outdone on multiple accounts by the penny. So, I would call that conclusive scientific results. And, yeah. So the question was, which will travel farther? A single lead ball or multiple pennies, both of them having equivalent mass. Now, what I came up with was that using a balance, 5 pennies was equal to, or as close as you're going to get, to 1 lead ball. Okay? So, what I came up with after that was that my hypothesis was that the lead was going to travel farther than the 5 pennies did. So, it was really surprising to me when I tested it, and my process to test it was to build a trebuchet, which I used a engineering kit for, and then the second step was to come up with a process to test it, and the way I did that was I had tape next to it, and the tape got stuck down, and then I would launch, and there was measuring tape right next to it, and it would stick on the tape, and then I would measure where it was on the tape or where it landed, and from there it worked out really effectively when I was working on that. And of course I would record my results, and then I marked on the floor next to the measuring tape where the variables landed, and it was really nice. My controlled variable was of course the floor, the measuring tape, where it landed. The trebuchet was a controlled variable, and of course the uncontrolled variables, the things that I changed, were the lead and the pennies. And I think that it worked out very well. the answer to my question was that the pennies travel farther. My best guess as to why is because I was taking averages, and if you looked at it, some of them didn't go as far, some of them did go as far, but the overall looked like it was just getting more of a transfer of energy. Now, of course, if I went and tried to launch something very large out of there, it wouldn't launch. And that's the interesting thing about a trebuchet, is that if you have more weight on something, it is quite possible that it would go not as far, because what you have with the trebuchet is you have basically a fulcrum. Okay? You have something here with weight right like that. And then you have another weight down here at your end that you're launching. And with the trebuchet, at the design that I had, when you had this weight here and it was launched, if there was more weight here, then this would actually slow how fast that went. So that might have been a factor, was weight, or it might have been air resistance. The pennies can slice through the air sideways, and that was possibly the ones farther out were going that. The ones further back were probably going something like that and getting spin. And with the lead ball, there were really consistent results, because if you turn a circle on its side, then it's not going to do anything. So, two examples of how that may have worked was, take a softball. A softball from any angle will travel through the air, and it's going to have about the same amount of resistance on the side. Now, a lead ball is almost exactly a softball, only it doesn't have the threads and the stitching on it. So if we have the same amount of wind resistance from all sides, then we're going to have a equivalent distance almost every time. But with an object like this, sort of a saucer shape, okay, when it spins, it's going to go very accurately like that. But if it goes like that, then it's going to have unequal wind resistance, and if it comes at an angle like that, then it's going to want to spin rapidly and lose control. So that might be why. Now, the final thing that I would have to say is that it was a very interesting project to do, and the scale that I used was inches, and of course the weight didn't have a scale, it was just a fulcrum scale. I'm not quite sure what the technical term is, it's just about like that. And that was, of course, the hammer. So at this time, I would like to have any questions or comments from the class.